Hello everyone. So, we will continue with the discussion of low stress mechanical characteristics. In last class, we have discussed the first module of Kawabata evaluation system, which is KESF 1, where we have discussed that the low stress tensile force, tensile characteristics and low stress shear characteristics, those can be measured by KESF 1 system, and here the specific specimen is stressed by rotation of the drum for tensile measurement, and by sliding the other jaw we can measure the shear characteristics. These details we have seen, and various loading conditions we have discussed, and also we have discussed different test parameters which we get in different form, and then we have seen the shear characteristics, different test parameters for shear characteristics, and these are the different parameters we get. Now, we will start the next module, which is KESF 2. The KESF 2, which measures the bending characteristics of fabric, low stress bending characteristics. Here it is not like the Shirley bending strength tester or like loop method. In Shirley bending strength tester, what we have seen, we can only simply get the bending rigidity once the fabric is hanging on its own mass, but that is not the exact situation for most of the handle related characteristics for functional textiles. For functional textile, suppose this cloth, it is bending not due to its own mass, we have to bend the fabric, and the fabric stiffness is actually it is due to the fabric stiffness we get the some pressure on our body, we get some handle characteristics. So, the principle here it is very close to actual application. Suppose this is the fabric sample, fabric specimen. Here the fabric is gripped by one jaw, okay, and other jaw which is actually movable like this. In this process we try to bend, and here the bending curvature it is fixed. The fabric is bent to a specific curvature, and up to that curvature once it is bent, then it again comes back to the original point, and then it is bent to the other direction. In this way the bending is repeated, and we get both the bending curvature and also the force required to bend the fabric. These two data we can get. So, the fabric specimen is gripped by two jaws here. So, this is the fabric specimen which is shown in black color. One jaw which is a steel wire. This is the jaw here, it is connected with the torque sensor, and another jaw it is connected with the bending arrangement. So, once this is moving, this bending arrangement is moving, the torque sensor will sense the required torque, and from there we can calculate the bending force. So, one jaw is attached with the bending arrangement as I have mentioned, and which moves in circular direction to apply the bending force. So, this is the steel wire with the torque sensor, and other side it rotates, it is a circular direction, it makes the arrangement is such that it rotates in circular direction to apply the bending force, and the other jaw is connected with the torque sensor, which detects the torque value of the steel wire during bendings of specimen. So, this will detect the torque value, and from the torque value we can get the bending force. The curvature of bending is obtained from the drive to the bending arrangement. Here it is a drive arrangement, and this drive arrangement will give idea, we can from the gearing arrangement of this drive we can calculate the bending angle, total curvature we can calculate. The fabric specimen is bent with the help of bending arrangement between the curvature of plus minus 2.5 centimeter to the power minus 1. So, that is the curvature limit. So, plus 2.5 to minus 2.5, again it goes in that way. So, if you see the animation here, this is rotating and it makes the system, the bending system rotates in one direction and again it come back to other direction, and this is the bending hysteresis curve. From here we can calculate the slope B, it is a bending rigidity B, which is a slope between 0.5 to 1.5, that is the curvature within that. So, this is 0.5 to 1.5, within that the slope if we take, it is called the bending rigidity. Another parameter which we get, it is a 2 HB, which is a hysteresis of bending at one curvature. This is at curvature limit 1 and this is the hysteresis. Okay. So, from there we get two parameters, one is the bending rigidity, another is the hysteresis which is 2 HB. So, loading condition and parameters measured for bending characteristics are rate of bending, which is 0.5 per second, that is the rate of bending. That means, if we have to have say 2.5, so it takes typically 5 seconds in one direction, another to come back again it is a 5 second and 5 second takes it is in other direction, 2 plus minus 2.5 it goes. Sample size is 20 centimeter by 1 centimeter. So, lengthwise it is a 20 centimeter and 1 centimeter is the effectively it is a 1 centimeter is the width. So, that way it bends, maximum curvature is plus minus 2.5. The test parameter as I have mentioned, it is slope between 0.5 to to 1.5, that curvature, it is a B, okay. It is a bending rigidity, and bending hysteresis at plus minus 1 curvature, it is a 2 Hb, is expressed in millinewton. So, from here we get two parameters B and 2 Hb. Now, the next principle is the it is KESF 3, which is actually the compressional tester. The fabric specimen is compressed between two plates, one is anvil, which is support plate, another is the pressure foot. The fabric specimen is placed on the anvil and pressure foot is actually lowered. So, pressure is increased with the help of pressure foot, while continuously monitoring the sample thickness by thickness detector. So, as I have mentioned here earlier also, that the loading and the total thickness, it is monitored during the loading condition and the unloading condition. The compressive pressure is detected by compressive force detector. So, one is the compressive force detector, another is the which monitors the thickness by the movement of the cross head, okay, pressure foot. Now, this is the schematic diagram of the instrument. Here this is the fabric specimen placed on the anvil. Anvil is connected with the load sensor, which detects the compressive force, and the pressure foot which moves up and down, which is controlled by the drive system of the pressure foot, and this rotation of this disc is measured by the thickness detector, which is the another transducer which rotates, which measures the angle of rotation. From there it calculates the thickness. Okay. Now, the system is that it moves down initially, and as soon as the predetermined minimum pressure is reached, it will start the drive will start rotating in other direction. So, pressure foot will move gradually upward and the pressure will reduce. So, we will get the complete curve of loading and unloading. From this loading unloading curve, we can calculate different parameters. Let us see the animation for this system. Now, the fabric is being placed between anvil and pressure foot. Now, the drive for the pressure foot is started. It is initially moving downward, and after reaching certain pressure, predetermined pressure, and it moves upward. So, in this way we can get the complete loading unloading curve. Okay. So, after and this loading unloading curve, this is the thickness is detected by this thickness detector, and this load, the pressure is detected by this load cell, and from this instrument, after getting all this total entire curve for loading curve and unloading curve. So, we get the values. Okay. So, here during loading, so initially this is the initial point, during loading the thickness increases, thickness reduces gradually. Here this x axis is thickness, y axis is load, thickness reduces gradually, and after reaching a certain load, the anvil starts moving upward. So, thickness gradually increases, and we get different parameters similar to the tensile test as in KESF 1. It is linearity of compression curve. So, linearity of compression curve we get from the, that is the value of area under the compression curve divided by area under the compression curve and divided by the total area of this triangle A T and T m. Okay. A T 0 and T m, this is the T 0 is the initial thickness and this is T m is the final thickness. So, A T 0 T m, this triangle. So, if this curve it follows the straight line curve, then it would have been 1. Okay. So, linearity of the compression curve is area under the compression curve divided by this area of this triangle, and W e is the compressional energy, which is nothing but the area under the compression curve. Okay. Compression curve, and R e is the compressional resilience, R c, R e is the compressional resilience, which is the area under the recovery curve by area under the compression curve. So, that way we can get all the data. So, here the setting and loading conditions are, the rate of compression is recommended as 0.02 millimeter per second, area of circular pressure foot is 2 square centimeter, maximum compressive pressure we can achieve, we can have here 5 kilopascal, which is not that high normally. That is why it is a low stress mechanical characteristics, which is used for to assess the fabric handle characteristics. Okay. 5 kilopascal, and the test parameters which we get here, the thickness compression, okay, as per the proportion of original fabric thickness, EMC is expressed in terms of percentage. So, EMC we can get, which is actually as per the initial thickness. Fabric thickness at 5 kPa pressure is TO, is expressed in terms of millimeter. Compressional energy at 5 kilopascal pressure is WC, is expressed in terms of joule per square meter, and linearity of compression curve LC is unitless because it is a ratio of area, and compressional resilience RC is actually expressed in terms of percentage. So, all these parameters we can get from the compression and recovery curve, and the last module of KESF is the KESF 4, where we measure the surface roughness and frictional characteristics. The fabric specimen kept at constant tension by hanging dead weight. So, fabric specimen we have to keep at constant tension, we cannot leave it loose, otherwise we will not be able to measure the surface characteristics, because fabric specimen has to be straight and gets to and fro motion from the drum, which rotates intermittently in clockwise and anti-clockwise direction. So, that the fabric, initially fabric we have to keep in tight by hanging certain dead weight, and one side its hanging dead weight is there, another side it's kept, it's fitted on a drum, and as drum rotates the fabric makes movement. Drum rotates clockwise and anti-clockwise direction. So, fabric also makes to and fro motion. Okay. In this way, the frictional force between fabric specimen and a friction surface. So, there is a specific friction surface is there, okay, at the friction point is detected by the frictional force detector. So, there is one point which is a frictional force detector is there. So, it is a force detector is there. So, which measures the frictional force. The probe of displacement sensor is in touch with the fabric surface. So, one is that frictional force detector, another sensor is the which is the displacement sensor, which sense the fabric roughness. As the fabrics, like this is the fabric, the displacement sensor is placed just it is kept on the fabric surface. Okay. If the fabric surface is smooth, there is no, there is nothing, it is a totally, it is a smooth surface. Once the fabric is moving, the displacement sensor will not make any vertical movement. But if the fabric surface is rough, now let us see, this is the fabric surface and displacement sensor is kept like this, it is placed on the fabric, and here this side the load is hanging, dead weight is hanging, and other side it is connected with the drum. Once drum is rotating, the fabric will make movement, and suppose this fabric is totally very smooth. So, there will not be any deflection of this displacement sensor. So, this will be stationary, it will simply slip on this, okay, slide on this, fabric will simply slide. But suppose the fabric is a rough one. So, in that case this displacement sensor, depending on the roughness, this will make up and down movement. This movement is recorded and this will show the surface roughness characteristics. That means, the probe of displacement sensor is in touch with the fabric surface. When the fabric moves in horizontal plane, due to the surface roughness, the probe deflects vertically. If the fabric surface is perfectly smooth, there will not be any vertical deflection. This vertical deflection of the probe is the measure of surface roughness of the fabric. So, once is that the frictional force is detected, another is the deflection is detected. So, we measure the both the frictional characteristics and surface roughness characteristics of fabric. So, the KESF actually measures the surface related characteristics. Now, this is the schematic diagram where this one is the fabric specimen, dead weight is hanging to keep the standard tension, certain tension, and here it is a friction point, it is connected with the a rod which is connected with the friction force detector. Okay. And another point here, surface roughness detector, as I have shown, which detects the deflection. Now, once the drum is rotating clockwise direction, so other side is free, this can simply move up and down. Okay. Once this drum is rotating in clockwise direction, there will be a friction generated at the frictional point, and this friction force is measured by the friction detector. And when the fabric moves in other direction, that is the rotation of the drum is in the other direction, there will be another frictional force. So, this detector, force detector, it works in compression mode and extension mode. Once the fabric is moving in the right direction, that is the drum is moving in clockwise direction, this friction force detector works on the extension mode, and once the fabric is moving in left direction from right to left, that is the drum rotates in anti-clockwise direction, this force detector works on the compression mode. So, we can get both the data, okay. And similarly during this movement we get another signal depending on the surface roughness. This detector, surface roughness detector moves, makes the deflection, vertical deflection, and we get the surface roughness value. Now, let us see the animation for this. Now, once we start, like drum is rotating clockwise direction and this is the surface roughness and here is the friction. We can see that it gives the friction value depending on the direction. Okay. Once it is moving, it is in the compression mode, it is giving in the other direction, in this way it gives. Okay. And here depending on the deflection, okay, we get this curve. In x axis it is a distance travelled and y axis it is a thickness. The variation in thickness we can get from this curve, and variation in coefficient of friction. In x axis it is a deflection, distance travelled by the fabric, and y axis the directly we get the coefficient of friction if we know the normal force. Okay. So, we get the geometrical roughness value by the hatched area of the hatched portion. If we get, it is the geometrical roughness value. Okay. And mean deviation of coefficient of variation, this is the area of hatched portion. So, that from there we can calculate the mean deviation of the friction, that is MMD, and also we can calculate the mean value of friction which is MIU. So, from there we can calculate the mean value if we have individual data. So, from this technique, from this module we get 3 parameters. One is SMD, which is geometrical roughness, MMD, which is the mean deviation of friction, and another is the mean value of coefficient of friction, which is MIU. So, all 3 parameters, as we know that these are related to only the surface characteristics of the fabric. Okay. That means, higher the roughness, higher will be the SMD, because higher will be this area. Okay. Similarly, that the MMD, mean deviation of coefficient of friction, is extremely important to judge the whether the fabric is touch, it is a scroopy feeling, whether there is any stick slip mechanism, that will give the value. Higher MMD value will show the scroopy feeling. Okay. So, let us see the loading condition and parameters measured for frictional characteristics. The setting and loading conditions are: the traverse rate of fabric is 1 millimeter per second, that is the traverse rate by rotating drum. Constant tension on fabric is 0.1 Newton per centimeter, that is a dead weight we use. Normal load which is applied at the friction point, 0.5 Newton, that is a normal load, it is a very small load is applied, and maximum fabric movement is 3 centimeter. So, that 3 centimeter it moves in, that is the maximum movement. And test parameter which we get in the frictional module, as I have mentioned, coefficient of friction MIU, which is unitless, which is, and another is that mean deviation of mu, which is MMD, again it is a unitless. Okay. And for surface roughness characteristics, the setting is the traverse rate of fabric is exactly same, because the same module we are using and we are testing in the at the same time, but the constant tension is again same 0.1 Newton per centimeter. So, we have to maintain the same constant tension. If we do not maintain the tension here, the problem will be that the fabric's wrinkle will show off in the result, which will give wrong result. And constant force which is applied 0.1 Newton. So, here we measure impart the constant force on the displacement sensor 0.1 Newton. It cannot, it should not be too high, because otherwise it will compress the rough portion also. So, we need a very small weight, and at the same time we need for certain load to keep contact with the fabric sample specimen. And maximum fabric movement, again it is 3 centimeter, it is exactly same to that of friction. And the test parameters and units, here we get the value mean deviation of fabric surface profile or geometrical surface roughness SMD, which is expressed in terms of micron meter. Okay. Now, from all these parameters, if we have which we have seen in Kawabata, we get 16 different parameters from all these modules, and ultimately this all these parameters are used to evaluate, to judge the fabric handle value. So, primary handle value we can get, we can extract from all these parameters. So, to obtain the primary hand of fabric sample objectively, a regression equation was used. Initially it was used by Kawabata, and subsequently it has been modified for different types of fabrics, and the equation is of the form of, this is the form where y is primary hand value obtained objectively. So, there are different types of hand expressions, I will just mention, I will give some example, and x I is the mechanical parameters measured by KSA value. So, x I we have seen various mechanical parameters related to tensile, shear, compression, bending. So, these are the individual parameters x I. Okay. There is 16 parameters selected from tensile, bending, shear, surface characteristics, structural properties of fabric. C0 and Ci are coefficients obtained from regression. So, these are the different parameter, these coefficients which are obtained from the regression equation. Mi is the average value, xi is the individual value, okay, and this sigma I is the standard deviation of xi. This is the standard deviation. So, using this equation we can get the primary hand values. So, I will give some examples. Now, suppose this is the, these are the different hand expressions like Koshi, Shinai Akasha, Shari. Koshi means it is actually not exactly the stiffness, but direct it is related to stiffness of fabric. It is not directly the bending stiffness, it is related to the stiffness, it is related to other characteristics also. Similarly, Shinai Akasha, it is not just opposite to the bending, it is not the directly flexibility, it is a flexibility with soft feeling, okay. And Sari, it is a crispness, some crisp feeling. So, that all this handle, primary handle related characteristics we can get from the the values, primary hand values like some mechanical low stress mechanical characteristics we can get from this value. Okay. Now, Cauchy, if you see the stiffness, it is related with the B. What is B? Here B is the bending rigidity of the fabric. So, it is actually positive, means it is a positively related, actually increasing direction, it increases with the increase in B value, that means, and its weightage is 37%. So, it is 37% positively related, that means as the bending rigidity of fabric increases, the Cauchy value increases. Okay. Similarly, the 2Hg and 2Hb and Wt, they are negatively correlated with the Cauchy. What is 2Hg? 2Hg is the shear hysteresis. So, it is a shear hysteresis, 2Hb bending hysteresis. So, as the shear hysteresis or bending hysteresis increases, the Cauchy value reduces. Similarly, Wt, tensile energy. So, as the tensile energy increases, the Cauchy value reduces. That means, it should be stiff enough, but the tensile energy should be less. So, we will get the higher Cauchy value. So, that way we can interpret the primary hand characteristics using the value which we have got from the KESF testing. Similarly, Shinai Akasha, which is a flexibility with soft filling. What is flexibility? Flexibility in terms of shear stiffness. That means, the higher shear stiffness will result lower Shinai Akasha. That means, if we want to have higher flexibility, so we have to have lower G value, that is shear stiffness. So, a fabric with lower shear stiffness will give higher flexibility. So, that is why it is this is related with, this is not that related with the Cauchy B value, but Sari is the crispness. What we have I have discussed now, it is a Sari, and Shinai Akasha, which is flexibility with soft filling, which is equal to that, it is inversely proportional to the bending rigidity, it is a 44%, it is related with the negatively related with the bending rigidity. That means, B, if it is if the stiffness is high, the Shinai Akasha will be low, it is that means it is making the fabric flexible. Similarly, mean MMD value, mean deviation of mu, if it is high, higher mean deviation of mu will give lower Shinai Akasha. So, it is negatively related, it is negatively related with the G value, it is a shear rigidity. That means, higher shear rigidity will give lower Shinai Akasha value. Okay. So, that is how, so higher Shinai Akasha means higher flexibility of the fabric. Similarly, Shari, Shari is the crispness of the fabric. If we see the crispness, it is if the fabric shear stiffness is high, that means it will be less crisp value. So, crispness we are getting from the G value, that is shear stiffness, that is it is negatively correlated, very highly positively correlated with mean deviation of mu. That means, a fabric with high mean deviation of mu will have crisp value. That means, the coefficient of variation is changing, that is why it gives the crispness value, and also it is related to some extent with SMD and RC. RC means compressional resilience. So, these are the values which are actually significantly related with these parameters. There are other parameters which are not that significant. So, these are the significant parameters. That means, the primary hand value, primary hand expressions we can get from the basic parameters which we get from the Kawabata evaluation tester. So, these are the primary values which we have got. Now, we will discuss the next module, next type of instruments, which is FAST, fabric assurance by simple testing. Now, we must understand the basic difference with the Kawabata system. In Kawabata system, which we have got, as I have mentioned earlier, the tensile side or loading side and unloading side, we get the data, entire data from each and every point through the transducer. So, the sensors which we get, which supplies individual data, and also we get data from loading direction as well as in the unloading direction. But the FAST system, it is very simple. Here we get a discrete value, discrete point. Okay. So, it has got, it is developed by the CSIRO Australia. It also gives the objective indication of fabric handle characteristics. It consists of series of 3 instruments. So, it has got 3 modules. FAST 1, which is compression meter, FAST 2, which is bending meter, which is similar to the Shirley stiffness tester, and FAST 3, it is extension meter. These are the 3 instruments. In addition to this, one test method is there, which is FAST 4, a dimensional stability tester. So, we will start with FAST 1. So, in FAST 1 compression system, which measures the fabric thickness. Although this instrument apparently looks very simple, but the type of data which we get, type of information which is get, it is very nice. The fabric thickness T is measured by the some pressure foot, which is measured at the pressure of 2 gram force per square centimeter and as well as 100 gram force per square centimeter. So, there are 2 pressures, at 2 pressures we measure the thicknesses, and the surface thickness ST is the difference in thickness of fabric measured at pressure 2 gram force per centimeter square and 100 gram force per centimeter square. Now, let us see the difference between this FAST system and the Kawabata system. In Kawabata system, this was the anvil and fabric sample was there and pressure foot. Pressure foot was moving up and down, and we are getting data from the pressure, that is the movement of the pressure foot and the load cell with the anvil. So, we get both the loading elongation, that is compression and recovery curve. But here the system is very simple. This is fabric specimen placed on a table, this is a table, fabric specimen here, and it is loaded with the certain dead weight and we measure the thickness here, and then we increase the load at certain. So, initially there is a smaller load, another, then we have increased the load and we measure. So, T 1 is the initial thickness and then after higher load it is T 2, and this difference between T 2 and T 1 we measure, and this is actually surface thickness. What is surface thickness? Suppose this is a fabric, it has got some hairiness on the surface. So, initially at lower load we measure the thickness. So, at load 1, and once we increase the load, suppose once we increase the load, these hairs will get compressed, mainly these hairs will get compressed. So, initially there was no compression of the hair, deflection of the hair, after and the load is not that high, which will not basically deform the fabric. This load L 2 will deform the hairs only. That means, the difference, this T 2 and T 1, it is not the deformation of fabric, it is the deformation of the hairs. So, that is how this difference, it is called surface thickness, which actually indicates the hairiness of the fabric surface. So, the surface thickness S T is the difference in thickness of fabric measured at pressure of 2 gram force per square centimeter and 100 gram force per centimeter square. It measures the basically it indicates the hairiness characteristics of the fabric, surface hairiness. So, surface thickness is the difference in thickness, as I have mentioned. Information on hairiness or surface bulk is obtained. So, in either hairiness or it is a surface bulk characteristics, not the bulk characteristics of the fabric core. So, this gives the characteristics of hairiness. So, another characteristics from the same parameters, that is difference between the thickness at 2 gram force per square centimeter and 100 gram force per centimeter square, we get another parameter which is called released surface thickness, STR, surface thickness released. What is that? It is a measure of surface thickness after the fabric has exposed to the steam or water, which is used to simulate the actual wear condition. Now, we must discuss here this part. So, we have got the surface thickness as I have mentioned. Suppose this is the fabric, original fabric sample, original fabric sample with some hairiness, some surface bulk or some hairiness. Now, what we have done? We have actually coated the fabric. This fabric is coated with some coating material, and where this is the coating material, where the hairiness, all this hairiness have come under this coating. Now, here if we measure the surface thickness S T, we will get a value say S T 1, and after that we wash the fabric or steam treatment. steam treatment we are giving or washing. So, which is simulating the actual wear condition. Suppose this the finish which we have applied, coating finish or finish we have applied, which is permanent, which is not washing out. What will happen? This fabric will, the surface will remain intact, okay. Hairs will not come out, and we will get value ST2, which is almost equal to ST1, very closely equal to ST1. Another fabric, suppose now we are keeping on washing and we are laundering and we are doing. What happen? This finish will come out, finish will come out gradually, and this hairiness will again come out, show off. That means, and again we are testing STN after nth wash. This STN will be more than ST1 or something. So, the difference in this surface thickness and this surface thickness, it is called, it is a released surface thickness, STR. So, released surface thickness and initial surface thickness, this difference will show the how well we have actually finished the fabric. If the finish of the fabric is perfect, if it is permanent, then the release surface thickness and surface thickness value will be exactly same or very close. If the release surface thickness is more, much more than the surface thickness, then it will show that the after exposing the steam or water, which is simulating the actual wear condition, the fabric is actually losing its finish, the finish is not permanent. So, we can see from very simple testing of thickness with two different pressure, we can get idea of fabric surface characteristics, and also this surface thickness will give us idea about the touch of the fabric. If it is, whether there is a hairiness or there or not, whether surface bulk is proper or not, we will get idea about the this characteristics through the surface thickness. So, the principle is that it is a simple principle, it is a normal load, pressure foot is there, and normal load we are applying, this is the fabric, and here is the surface thickness, only at the surface level we are, it is compressed. And the next method, it is a first two method, which is bending meter, and bending meter measures the bending length and bending rigidity of fabric. The bending length and bending rigidity, it is exactly same as the Shirley stiffness tester. The fabric bending length simulates the draping behavior of fabric, and the bending rigidity is related to the quality of stiffness when a fabric is handled. Okay. So, that is how we get the fabric handle characteristics. A very flexible fabric, like very low bending rigidity, may cause seam puckering, while a high bending rigidity fabric can be more manageable in sewing and so produce flat seam. So, it gives idea about the seam puckering and stitching condition. sewability of fabric, the operator error of aligning the sample. So, here one optical sensor is used while aligning the sample. Sometime the during testing the alignment, if it is wrong, that will give us wrong result. Here optical sensor is used for proper alignment of the sample. Okay. The principle, as I have mentioned, it is exactly same as the Shirley stiffness testers, which we have used earlier. The angle here which is used same as Shirley stiffness tester, 41.5 degree, and it's we measure the overhanging length, and from there, from overhanging length we calculate the bending rigidity of the fabric. So, we will stop here for today. We will continue with this first testers, first 3 system in the next class. Till then, thank you for patient hearing.